And we are live. Welcome, everyone. You can see a couple of people joining us there in the waiting room. Great to see you all. A couple of familiar faces, a couple of new ones. Welcome. If this is your first session, I will just let you know that we record all of our webinars and they are all stored on the Verisian network, which you can find on our website. It's a free membership and you can go on there and look through all of our previous webinars in the resource library. If we cannot get round to your question, we'll be hosting a Q&A session at the end of this. But if we can't get round to your question at the end of the session, or you are watching this on demand, do reach out to myself or Brandon, and I'm sure he'll be happy to answer any questions you do have. Do let us know where you're watching from in the comments. It's always nice to see where everybody is watching from today. But without further ado, I will make a start. So with me today, I have Brandon Bethel, who's an assistant professor of oceanography at Small Island Sustainability in the University of Bahamas. And he will be sharing with us the topic of the implementation of an extreme wave early warning system in the Bahamas. So Brandon, would you like to begin for me?
Yes, good morning, good evening, and good night to everybody. Very happy to have you here. What I'll do is to give you a more or less very brief overview as to what we intend to do at the Glass Window Bridge on the island of Eleuthera in the Bahamas. And so we can begin. So the presentation will just take into consideration 7 sections. We'll have an introduction, early warning systems, oceanographic buoys, high-frequency coastal radar, ocean wave models, the implementation of said early warning system, and a conclusion. And so we can begin. For those that are not familiar, the Bahamas is an archipelago that lies it's in the Atlantic Ocean, yes, but we are politically affiliated with the Caribbean nations, while not technically in the Caribbean Sea. But we are north of Cuba, about south of the United States, and we have a population of about let's say 350 to 400,000 people. It's not very much, but we do call it home. What is important for us, however, is that on one of the islands, Eleuthera, there is what's called the Glass Window Bridge. And while it is very picturesque, it is, however, a place where communication between the northern and southern parts of the island happens, which means that it experiences a great deal of traffic every single day. Now, because of its extreme proximity to the ocean, you can then imagine that it is subject very strongly to what the ocean and the atmosphere are doing at any one time, let's say on a local scale, so just around the bridge, and also some distance away. And so we can see this video here of extreme activity. Is that a play? So what you all just saw was an example of extreme wave activity at the Glass Window Bridge. You can tell from the imagery that the local weather does not suggest that extreme wave activity should be occurring at all. And so typically, despite the fact that the local population is well aware of this activity going on, foreigners who are visiting, who are exercising their right as tourists near the bridge, they often do not know. And so you then have issues like this. Now, one way that we can know that this is indeed a problem is that it has been a consistent problem throughout history, where this most recent event was on March 5th, 2018, but it's not just people that are at risk, of course. It's the incoming traffic that is also a problem. The infrastructure of the bridge is corroded away on a massive scale due to the frequent wave activity there. And so there is plans now to move the bridge slightly westward to be out of range of the extreme wave activity. However, this also presented us with an opportunity to prevent additional issues at the bridge in terms of people getting hurt because they don't know that the wave activity is about to occur. Again, the local weather conditions did not suggest that let's say, for example, during a hurricane where you would know that it is not safe to be, let's say, traveling the bridge or in coastal areas, local weather did not suggest on that day that wave activity would have been a problem. And so that then motivated our work here. So we can then move into a very brief discussion on early warning systems. And in essence, you would have a general set of observational platforms, whether they are in situ or they are remotely sensed, by which you can observe what the ocean is doing at any moment in time for a variety of variables. And we're not just considering the oceanic variables, but the meteorological ones as well. So you would then imagine that you have a series of buoys, satellites, seagoing ships that would then observe waves, wind, temperature changes, what the ocean currents are like. Almost any variable you can think of would all be counted within an ocean observation system, and this is what we want to build. And so in the next few slides, I do intend to briefly go over the individual components of the early warning system we want to implement. But I'll also then describe how all of those will be integrated, as you see here in this image, together for one extreme early warning system for those extreme waves at the Glass Window Bridge. So one thing that we need to understand is that the early warning system is going to leverage the data that we collect, both in terms of the atmosphere and the ocean, to understand what rapidly changing conditions are going to be like, and then do some forecasting so we can prepare people. And so your early warning system is typically comprised of 4 elements. That would be the disaster risk knowledge, detection, monitoring, analysis and forecasting, warning dissemination and communication, and preparedness and response capabilities. Clearly, here we are concerned primarily with elements 1 and 2, where we'll have an awareness of what those disasters could potentially be. But more important than that, we will then engage in the detection, monitoring, analysis, and forecasting of this, and then to disseminate that information in a timely fashion, not just to the local population, but the entire island, if not the entire country, so that Bahamians in general and residents of Eleuthera in particular can be more aware of their environment and how their environment could potentially affect their lives negatively. So an example of, let's say, an early warning system can be found, let's say, in Indonesia, where one of their major considerations would be earthquakes. And so when an earthquake happens, you would then have a series of tide gauges, seismometers, which would have detected that event initially. And then that information is sent out by GPS satellite to communication satellites to everybody else, where that information can then be put into a system where you can simulate what is likely to happen in the near term, and adequately inform people on how can they say best be aware of what's going to happen, and then take some measures to minimize losses in economic productivity and their own livelihoods. And so this is something that we want to do here for the Bahamas, but it's going to be in a slightly different way. So what we're going to be doing now is principally looking at the extreme waves of the Glass Window Bridge, and the system will be built from the acquisition, deployment, and utilization of an oceanographic buoy and a high-frequency coastal radar to acquire both in situ and remotely sensed data. So on the left-hand side, you see an example of a buoy that would be placed some distance off of shore, and then you have a high-frequency coastal radar which is placed on the shore to provide information on a very large scale, as opposed to buoy, which is on a very small scale. And from each of these, we are interested in the wind speed, wind direction, the significant wave height, wave direction, wave period, and the current velocity. All of these now will go into understanding what the ocean and the atmosphere is doing at any one time in the current period of time, but also when now we can project that slightly into the future, what conditions are likely to be. So we've spoken of the observational systems which would provide the initial set of data that we're going to be using. However, they have one key issue. Although they can provide near real-time information, they absolutely cannot do any forecasting of any kind, which then means that you have to incorporate a numerical model into the system so that you can, using information from the past, let's say maybe 10 years of past information. We can then work out what the mean conditions are like. Then we can get information from the buoy and the radar and say, well, what are conditions now? And integrate that all into one numerical model and say, well, based on what the wave conditions, what the wind conditions were like in the previous day, the day before that, or the day even before that, what is it likely to be in 24 hours? What is it like to be in 72 hours? What is it likely to be in a week's time? And this now is where an advantage can be derived in that the wave activity at the glass window bridge would no longer be an event that people discover at the moment that they happen, right? And this is why, of course, the man had found himself on the bridge during extreme wave activity and was unfortunately pushed off the bridge and was severely injured. We do hope that with the moving of the bridge from where it currently is, slightly westward, we'll try to alleviate that issue. But also, if you would have the early warning system in place, then this can be avoided entirely, where the bridge can be closed down in the event of extreme wave activity, so that the likelihood of damage or loss in life can be reduced even further. And so when we now incorporate our numerical wave model, the forecasting will allow us then to project ourselves sometime in the future and provide up to the hour projections as to what the weather is going to be like, so that we can inform, let's say, island administrators, the authorities at and on Eleuthera, to close the bridge down before disaster occurs. So for this wave model, we are of course interested in the significant wave height, wave direction, and wave period. The work that is being done here is based off of a recent publication of mine. This is actually my PhD work, and so believe me when I tell you that this is something that has been on my mind for quite a number of years. It is a problem that I first encountered in 2016 when I was doing my last year of my undergraduate. And so when I saw a similar video of somebody else being pushed off the bridge at the glass window bridge, I knew that wave activity was something that was of high priority, not just for me personally, where it was interesting from a scientific perspective, but its applications have real world consequences. And this is something that we covered here in this paper here. And so we will then be running the numerical model based on the settings that I'll describe later on. So we can then go into a brief discussion as to the oceanographic buoys that we intend to use. So for those that may not necessarily be familiar, oceanographic buoys would simply be platforms that are placed out in the near or far shore that contains an array of sensors. And these, of course, would include sensors for the wind speed, wind direction, air pressure, relative humidity. Then if the appropriate sensors are in place, you can get wave height, wave direction, ocean temperatures, all of these different variables that can be derived from this very simple platform. And the key point of it is that once you have satellite communications engaged on the buoy itself, you can absolutely, following some efforts of quality control, get a real-time understanding as to what the ocean is doing at any point in time. And ultimately, this now is going to serve as the crux of what observation is going to be done at the glass window bridge. Next would be the high-frequency coastal radar. Now, one of the issues with the buoy, despite the fact that it does provide very, very good data, is that it is unfortunately stuck to one location. You do have some buoys that can float from place to place, but in our application, we want it to be anchored in one position, which means that its ability to understand what the oceanographic conditions are like are limited in terms of its spatial resolution. It will only know what the waves are like in that one point. Now, you may generalize it to, let's say, some tens of meters out from that one buoy, but ultimately you're going to require a great deal of them if you're going to cover the entire island. To get around that now, we're going to use high-frequency coastal radar. Now, it won't be able to give you, let's say, that level of accuracy as a buoy could, but it will get very, very close. But more important than that, it will also give you the ability of looking at those properties on a very wide spatial range. And so you could imagine that if your buoy is limited to just one location, that will give you good information, yes? But if you then superimpose on that buoy information, the radar information, you can then say that over a, let's say anywhere from 250 meters to over 15 kilometers of ocean, you can monitor all at the same time and get that information in near real time. So every 10 minutes to an hour, you can get an update as to what the ocean is doing, which means then that if this system was incorporated at the Glass Window Bridge, we could not only specify, let's say, over which days wave activity is expected, but we can get down to the hour. And this now is something that is going to be absolutely crucial to ensure that the bridge can be used as it should be used on a day-to-day basis, but it can be done so safely. And if we have to close the bridge down, we can close the bridge down not for an entire day, let's say to, say we're going to be safe here. But now, because we can get every 10 minutes to an hour, we can say, well, between the hours of 4 p.m. and 6 p.m., we'll close the bridge down because we're expecting high wave activity during that time. Once that event is more or less over, we can then reopen the bridge, and so that communication can continue at Glass Window Bridge with very little additional problems. One thing that we do have to mention, however, is that there are different kinds of radar that we can use here at the Glass Window Bridge. And so typically you may see them being subdivided into microwave radar coverage or high frequency surface wave radar coverage. And obviously, if you are the bridge, you want to be able to extend your observations as far out into the ocean as you can to increase the amount of time that you have to make the forecast, to do the quality controls, double check, then triple check, then send out the information to relevant authorities and also update the local population on what the ocean is doing at any time. And so we now have to make a trade-off, let's say in terms of where the buoy is going to be, because the further out to sea it is going to be, it then means that the more expensive it would be to moor it into place. But it will give us more time. The radar, by contrast, will allow us to stay in the same safe location on land, but still push ourselves several kilometers out to sea to increase the amount of time that we will have to make these predictions, to make these observations as to what the waves are doing. And so in our first iteration, we want to have a high frequency coastal radar out to go as far out as possible. But then over time, we're going to then hopefully find the budget to have microwave radar coverage close to the shore to get even higher resolution information. So we can not just, let's say, provide information based by the hour, but let's say every 10 minutes, that we can give you a refresh rate. And so that the amount of time that the bridge is potentially closed to traffic due to extreme waves can be reduced even further. So we then ask ourselves, what kind of trade-offs will occur if we choose, let's say, the coastal radar or the microwave. Now, typically, if you were to choose, let's say, a radar that is near to the ground, it means that your ability to see far out into the ocean is going to be limited because, of course, the Earth is curved, which means then that we would have to have, again, another trade-off between how high the radar antenna is and how far out we want to see. And so there are quite a few decisions that have to be made in terms of the selection of radar that we use. And that now, of course, is explained more clearly here in this table. So on the first column where it has the frequency, you can see that it starts off with a lower frequency and then progressively gets higher. But at the far right of the image, the maximum wave that can be observed by that particular frequency also changes. And so we would have to, let's say, in selecting which radar we're going to use, not just choose these in terms of the distance that we want to get information from or the resolution that we get things at, but instead we want to now find a balance between what the resolution is going to be like, what the maximum wave heights we can expect are going to be, and then choose a radar adequately. This, of course, now is not a simple matter, and the reason why it has taken quite a while to get here is because a lot of the background research to make this selection happen has only just been done. In terms of the research paper I produced just a few months ago. So once you have that information, then we can move ahead forward into the ocean wave models that we want to use. So as previously mentioned, we want to use a wave model, a numerical wave model, and those now simply calculate the spectral action balance equation and push that forward in time. And so that equation now, while more or less complex, the most important part would be the source terms, where you would have wave growth by the wind being considered. You'd have nonlinear transfer of energy between different 3 and 4 wave interactions. You have dissipative forces like wave decay due to white capping, due to bottom friction, due to wave breaking, all being considered within the single wave model. So that once now we provided an input of what the atmosphere is doing either in the past, present, or what we think it will be like in the future, we can then estimate what the corresponding wave field must be like once we now give it also bathymetric data to consider. So this will provide an example here. I did a very early implementation of Wave Watch 3 in the Caribbean Sea during Hurricane Matthew that occurred in 2016. This is an example of the bathymetry that was used. But here now would be the wave fields that were considered for that time. You'll see also that you have a few buoys that you can now use to estimate just how accurate your model was. And so when I made mention of the buoy before, the buoy wasn't just meant to provide observations of the ocean at any given time, but instead it can also be used now to quantify just how effective our modeling efforts was in predicting these wave events. So here now is an example of it. We ran the model between September 28th, 2016 to October 7th, and here is Hurricane Matthew based on the Wave Watch 3 model. You can see that it, of course, entered the Caribbean Sea and then stayed within the central Caribbean Sea, but while the GIF doesn't show it, it then moves up northwards. But what's important here is that the model resolution for this one is very low, only 0.25 by 0.25 degrees. And the bathymetric data was ETOPO1, where although it is used globally, its resolution in the Caribbean Sea is very, very poor. And that you can see from the amount of white spaces that occur near to large land masses. So for the islands of Hispaniola, Jamaica, Puerto Rico, then you have Central and South America, there are white spots all around the land masses, which means that there's no wave information whatsoever. Unfortunately, people don't live in the wide open ocean where this model now can provide information. They unfortunately live on the coastline, and so we have to then increase the model resolution quite significantly to get the small scale data. And that was the justification for what we did in our SWAN wave model. But here you can see that the peak wave period during Hurricane Matthew also peaked, let's say, not necessarily where the hurricane has left, but where it is about to go. And so you have a progression of swell radiating out from the hurricane on its way to different coastlines. But again, as you can see from the white areas around the land, wave information is not captured by the model at all, which means that it is more or less not a good idea to rely on such a low resolution bit of information to make your forecast for a particular geographical place that of course would be on the land. So to get around that now, we've changed the settings. We've changed the model, we've also changed the settings. The integration time covers, it has covered the Matthew event, but we've changed the model resolution significantly. So instead of 0.25 by 0.25 degrees, we've gone up quite a few orders of magnitude to 0.02 by 0.02 degrees. And also we're using the JEBCO product rather than the ETOPO1. And you can see there in the table provided on the right-hand side that the grid size of JEBCO is significantly larger than those of ETOPO1. The data points that is available in JEBCO is one order of magnitude larger. And so you can then imagine that our ability to forecast and model and forecast wave events very, very close to shore would be far better than what is publicly available, let's say using global wave models such as Wave Watch 3. This now would be an example from the ocean modeling publication. You'll see that every inch of the Caribbean Sea is covered by the wave model. And this means that we can go down to very, very small islands and say, well, for this particular island, the wave conditions are likely to be more or less accurate as to what the wave model is suggesting, because the bathymetric product has ensured that information can, that wave transformation can occur as it should occur because of the high resolution of the bathymetry that you're dealing with. And so one thing that I try to explain to my students is that although the wind is a primary factor to consider when you look at wave growth, the topography, the bathymetry over which the waves flow is also important, simply because when now you consider shallow water versus deep water, there is a difference in what the waves are going to do. And so once now you have a good representation as to the bathymetry of your study area and your wind information is good, your modeling results should also be good. And this is what we attempted here in this publication. So going back to the Hurricane Matthew example, unlike before where we use a low resolution wave watch 3, we've chosen a far higher resolution for SWAN. And in this example here, we averaged about 3 days of Hurricane Matthew's information, and we superimposed on front of this image of the wave height, also the buoy locations. One thing that we did see is that when you calculate the swell energy weight, and that would be the ratio of swell waves to wind waves, you would find that your wave field in the Western Caribbean Sea, let's say around 80 degrees west, would be comprised almost entirely of swell waves. But because of the presence of the Nicaraguan rise, most of that is being trapped within the Caribbean Sea, let's say under the 20th degree line of latitude. However, there is a gap between the Nicaraguan rise and the island of Jamaica, which allows waves to propagate on a, never each short reach, northwestern trajectory towards the buoy NDBC 42056. And so I could remember the day when this particular result came out. When I saw it, I said, oh, if this is the case, it means then that if I were to go into the historical records for this particular buoy, that's NDBC 42056, I should be able to find an increase in the wave period, which would indicate the presence of swell without a corresponding increase in the wind speed, which would have suggested, by contrast, wind waves. And I figured, why shouldn't I go ahead and do that? This is what science is. You should be able to make testable predictions that if your hypothesis is correct, going into the data, you should find exactly what you look for if your hypothesis has credence. And so I did it. I went to that particular buoy and I found the section of time in which that wave activity was likely to occur. And so you would see that between September 27th and October 1st, before that hurricane got near the Central Caribbean, the dominant wave period, that is the wave period associated with the highest energy of the wave field, was about, let's say, between 4, 6, let's say 7, 8 seconds maximum. These are wind waves, nothing to worry about. It's fine. But then suddenly, after October 1st, that dominant wave period shot up from that 4, 5, 6, 7, 8, straight up to 15. And it stayed that way for a significant amount of time, which means then, of course, that because Hurricane Matthew, after it entered the Central Caribbean, went on a northward trajectory, one would not expect, let's say, wind waves to have an effect beyond that slight trajectory beyond Jamaica. However, that swell would have retained itself for quite a significant time. And so even when we go back, we can then see that the swell that was captured by the presence of the Nicaraguan rise did not affect, let's say, the Central America specifically, right? Instead, it was allowed to flow very freely towards the Yucatan Channel to then experience, let's say, wave transformations. That swell propagated towards NDBC 42056 to, I think it was maybe Honduras, if I'm not mistaken, to then wash upon the shores of Honduras or the southern shores of Cuba. That swell event absolutely could have been predicted in advance. And so the residents of those particular coastal areas could have been given very, very precise estimates, not just on where those swell events were going to occur, but more importantly, when. That now, of course, ensures that when we do our work for the glass window bridge, this profile is what we're looking for. We're looking for a rapid increase in the wave period without an increase, a corresponding increase of the wind speed. That is a very clear signal for swell, and that is something that maybe you can tell from the excitement in my voice makes me happy. It means then that we can have confidence that this work is going to work. So if, let's say, for example, one was not inclined to believe me on the power of a numerical model in making these forecasts and making them right, this now would be the same extreme wave event at the glass window bridge, except we've also considered the entire surrounding region of the northern Bahamas, and we've used a numerical wave model to do so. I've highlighted the glass window bridge, I think, in a very small yellow triangle. Let me see if I can get my pointer out. Let me see if I can get my pointer out. Where's my pointer? Do we have a pointer on this? Yes, we do. Right, this is also red. We don't have another color. But the glass window bridge is right here. And so what you can imagine, of course, is that when you look at the swell energy rate, the closer that this number is to 1, the greater proportion of swell there's going to be in that wave field. So on March 5th, 2018, the same day as the video I showed you at the start of this presentation where the man was on the bridge and he got pushed off, you will find that the wave field out in the Atlantic Ocean on the eastern side of most of the northern islands there was simply swell, nothing but swell. And we need to be able now to not just, let's say, do a hindcast of this event as we did in this example here, but forecast this so we can know a day, 2 days, maybe 3 or 4 days in advance what the wave conditions are likely to be like, and then warn people on those eastern coastlines of the easternmost islands in the Bahamas that those swell events are coming, make preparations, stay away, and be safe. But also important, of course, is that the northeastern Providence Channel, it allows waves to propagate very freely on the inside of the archipelago of the Bahamas to affect the northern coastline of our capital island, New Providence. And so typically you would find that sometimes you would have high wave events on the northern coastlines of New Providence, and sometimes it comes as a surprise to locals and foreigners alike. I assure you, there's no such thing as surprises when it comes to the ocean wave field, because we could have predicted that days in advance once those numerical models were active. And this now ensures that we can minimize the amount of surprise that our residents face when dealing with the ocean. This is something that once we prove, we can make the proof of concept at the glass window bridge, we can instantaneously provide the same level of results anywhere, both in the country or in the region. And that is something that we have full intention to do once we are finished here at the glass window bridge. These annotations are still here. How do we remove them? Oh my gosh. Let me see. Well, we'll leave them for now. So we'll move on to now how we're going to incorporate those early warning systems, the components of the early warning system together. As mentioned before, we're going to have the buoy on the left-hand side, the coastal radar on the right-hand side, but also the numerical models above. But all of that now has to be integrated with a high-performance computer. It's not just a matter of saving the data, storing the data for future use. We also have to have the capability to process that vast quantity of data. Now, the buoy and the radar are going to put out text files. Those are going to be very small, 1 megabyte, 2 megabytes tops. That's not what our concern will be. Instead, the numerical models will be pushing out maybe 15 gigabytes worth of data every single day that we run a 7-day forecast. That is something that's going to require a vast quantity of storage capacity and a processing power to match. Let me see if I can try to remove the annotations. Let me see if I can try to remove them before we continue. Yes, there we go. Yes, so moving on. So as mentioned before, the observational platforms are going to provide near real-time oceanographic and meteorological information, but we also want to make sure that they comply with the global basic observing network standards, let's say in terms of our data, so that we can now share this data with any and everybody instantaneously. but also then we want to use high performance and cloud computing systems to use high resolution numerical wave models for the 7-day forecast, in addition to data processing, storage, and a distribution for both model and observational platforms. Now, beyond that, once, let's say we have an abundance of observational data and we have the model data together, we can then use the observational data to validate what the numerical model is saying. Yes, that is its primary purpose. However, if we also were to do something called data assimilation, that would be to take the observations from the ocean, from the atmosphere, and incorporate those into our numerical models. We can increase the accuracy of those models quite significantly so that we can minimize room for error even further. So you can see then we have multiple overlapping layers of how we're going to get our data and how we can ensure that our data is trustworthy. I understand that, of course, the most exciting thing for a scientist would be that data, right? Data is a be-all and end-all, but data doesn't mean anything on its own. It is only when you have the ability to convert that data into information and that information into knowledge can we pass that knowledge on to our disaster risk management experts or to the local population. This is something that the Bahamas Metropolitan is very good at, and we do hope to rely on their expertise to make sure that this project works, and it works very well, not just for the benefit of the Bahamian people, but for those throughout the Caribbean as well. So we've gone over most of, let's say, the text version of what we're going to look at, but now graphically I've shown you what we intend to do. So the sun in the center of this image here is the approximate position of the radar. The circle, the radar coverage now will show, and it's not the scale. It'll show that what the radar coverage is going to look like. And you can see how it overlaps with the position of the buoy itself. Now, the green arrows show the general prevailing wave direction. And so as waves propagate towards the shoreline, they will then enter that radar coverage. The radar coverage will then tell us, well, there is likely to be some events going on. Let's spend some more attention on it and monitor it. Once now we get a warning with the radar, we can then say, well, we expect the wave properties to be X, Y, and Z. That means that over a period of time, those waves are meant to hit the buoy where they can be observed again. That is a second layer of defense. That then tells us, okay, this is a wave event. Yes, it is an extreme wave event, something that we are interested in. It has X, Y, Z property. I want you to confirm those results with the buoys so that not just your remote sensing option tells you there's a problem, but your in situ buoy tells you there's a problem as well. So we have two ways to independently validate if this wave event is going to actually affect the glass window bridge. Now, I say this to say that the reason why we have both of these is because either system, they have both advantages and disadvantages. The buoy, as I mentioned before, will only look at oceanographic conditions in that one point, but the radar will be able to look over a wide spatial range. However, the radar stage will only be able to measure the most energetic signal, which will either be swell or wind waves in bimodal seas. The Atlantic Ocean, where we're looking at, is a bimodal sea, so that where we have, let's say, intense wind waves, let's say, for example, during a hurricane, we may miss swell conditions there because the radar will capture one or the other. It is black and white for the radar. The buoy is different, however. It will measure the full wave movement. It will be able to tell us if it is wind waves or swell or both mixed. And once we can ensure a significant difference in distance between the buoy and the high-frequency coastal radar, the difference between these two can become more noticeable. Then we can then be able to better discriminate what the buoy is saying versus what the radar is saying. But it is important to note that the discrepancy between these two does not necessarily mean that one or the other is not working or it is unavailable. However, due to the way that the measurements are made, it means that you have advantage X, Y, Z, for the buoy, but then you have the associated disadvantages, but then you have advantages P, Q, and R for the radar, which would be separate and distinct from the buoy here. And so having both of these systems in place, it means that where one does not have the advantage of the other can take over. This is very, very important. Now, despite those differences, you can look at how close the wave measurements from a radar and a buoy can be. Of course, it's not a perfect one-to-one correspondence, but within our field, this is already fantastic. We could not want anything better than this. And so we can then imagine that having both of these systems in place, while going to be very expensive, I can assure you that expensive, it will, however, be worth it. It will be justified. So what we did now is to go into that 10 years of modeled data that we have from the publication in Ocean Modeling. And we can see that on the left-hand side, you will have extreme waves, the extreme wave event of March 5th, 2018. You would see that the SWAN model results are in red, but the observations from the buoy are in blue. While again, not a perfect correspondence, you can see, however, the model was able to more or less accurately reproduce the extreme wave event, but the error was significant. So the mean average percentage error was at almost 20%. This is quite a bit, but we can still get a good appreciation as to what the wave conditions are like. And important for the discussion here is that the buoy observations recorded waves at a maximum of about 9 meters here. Now, that was the extreme wave event. That was due to an extratropical cyclone occurring deep in the Atlantic Ocean. Something a bit more close to home would be a simulation of Hurricane Dorian in 2019. And what was important here is that we got a snapshot of the hurricane just before it made its September 1st landfalling. And so you'd see that here, the significant wave height could have been measured at about 12 meters far offshore. So we can get a pretty good understanding, let's say, what the extreme wave activity, let's say the significant wave height from the extreme wave activity is likely to look at either during non-local hurricane conditions. So this was an extratropical cyclone here versus what an actual local tropical cyclone would look like. Both of these numbers are going to be very important. Where? Back to the table that we were looking at before. So I made mention that we have to make a compromise between, let's say, the range, the distance over which the radar can see, and the size of the waves that they can observe, and the resolution in kilometers that we can have. Based on the previous observations of, let's say, significant wave heights during the March 5th event, you can see that the waves were peaked about 9 meters, but during the hurricane activity, it's about 12. And so we want to now choose a radar that would incorporate all of those possible events. And so waves in the Caribbean Sea, typically anywhere between 1 to, let's say, 3 meters tops. But during extreme wave activity, this may rise, as we can see in the previous slide, all the way up to 9 meters, 12 meters in hurricane conditions. And so there we can choose a radar, let's say at about 13.5 megahertz, because it will give us a good balance in terms of the maximum waves it can observe and the resolution it can have and the range over which it can see. This now is what I think, at least on a preliminary basis, what we should do when it comes to selecting a radar and the frequency at which it will operate as. So again, the buoy will be able to look, let's say, just in that one point. But now with this particular radar, we can then see we can look out 60 to 90 kilometers out on a 3-kilometer resolution. That would be very, very good to ensure that our observations of the ocean system are very, very good. And it comes at the best possible, let's say, efficacy at the cheapest price. Because of course, the lower frequency you get, and the higher waves you can observe, the price is going to go up. And so we want to try to have a balance between both our budget and the needs of our local oceanographic conditions and the people that depend on them. So once we've spoken of, let's say, our observational systems, we can then imagine what our numerical model computational domain would be. I previously mentioned that we have the entire Caribbean covered, but if now we were to just consider the Bahamas, we would want to reduce the computational domain quite significantly so we can increase the resolution of the model itself and keep a balance between, let's say, computational resources and the efficacy to our forecast in terms of time, the resolution, the spatial resolution it will have, the temporal resolution it will have. So typically you would have, let's say, you would have the model producing output every hour. But if we're looking at a computational domain this small, it means then we can get potentially information every 10 minutes. And so, as I mentioned before, yes, the buoy will be able to give us information on a very timely manner, the radar as well. But we can overlap that also with the numerical model and keep those times more or less the same. We can have cross validations going on constantly and again in near real time. We can have the data assimilation, updating the numerical model just a few steps behind, let's say, what our forecast horizon is going to be like. This is what we want to do here. We also have an opportunity using this computational domain, not just to take advantage of our buoy that we'll put into place, but also buoys from the National Data Buoy Center that are run by NOAA. And so these are potential partners in our work here. But other potential partners, of course, would include the Bahamas Department of Meteorology, the Turks and Caicos Islands National Weather Service, and the Cuban Meteorological Institute. All three partners now can immediately benefit from this research, and we do hope that once the Glass Window Bridge serves as a successful pilot project, we can then do this research again, more or less cut, copy, and paste into other areas around the country and around the region. So I've mentioned quite a few times that the amount of data that we're going to be required to consider will be significant. Here, we plan to use both an in-situ computer, as in to have the hardware, let's say, in-country in a safe place, and we plan to use cloud computing. The in-situ computer will be coupled with an uninterrupted power supply so that, you know, whether power goes on, power goes off, the system will continue to run safely. We can also try to feed it with renewable energy to reduce the carbon footprint of the project, but the cloud computing option now would mean that even if our local system goes down, the forecast can continue. Data will be backed up both in a physical location under our direct control, but also on a cloud computing server, so that if something were to go wrong for any reason, we will always have a backup that we can tap into to keep the forecast continuing. So here is the conclusion. We aim to build an early warning system for the Glass Window Bridge. We feel as though that this would be an absolutely vital part of the infrastructure that is going to be put into place during the construction of the new bridge. And we're going to use buoys, remote sensing, numerical models to build that early warning system to protect lives. But of course, none of those systems will be able to protect the infrastructure itself. But in a future research project, you can imagine that once you have accumulated sufficient information from the bridge, you can then work with coastal engineers to design a way to shape, let's say, either nature-based solutions to reduce the amount of incident wave energy at the bridge, or to bend, to refract the waves away from the bridge entirely. And that now can be done once we have the data coming in from the buoys, the radar, and the numerical model all at the same time. Once we've done that, we would have make a significant step towards building what's called a digital twin ocean. And this is simply a computer representation of the ocean, which would have combined ocean observations and advanced numerical modeling together. So we'd have real-time virtual representation of the ocean and the atmosphere at any one time. This, I think, is the ultimate goal. And if we can make this work here, then expanding the network to make a digital twin Caribbean Sea model would be something that we can, that would be instantaneously possible. So this is the list of references that I used in this study here, and I can now take questions.
Excellent. Thank you very much, Brandon. We do certainly have some questions already, but if you do have any more, pop them in the chat or the Q&A. I'll start with Dr. Davis, who has two questions. What vertical elevation would a surface wave radio tower need, and what anchorage would you need for the buoys?
Well, I'm going to answer the buoys first. The anchorage will depend on what the seabed is like at that location. We aim to put the buoy in about 250 meters worth of water, but I don't know exactly what the bathymetric profile, let's say the sedimentology, the marine geology of the area is like. So we can't really answer that question yet. We would have to do a study. We'd have to go out to the site, get let's say some soil samples of the area before we make that determination. Then, with regards to the elevation of the radar, that is going to be dependent on the eventual height of the bridge itself. That now has not been finalized, so we can't really answer that question either. It is only after we've moved some ways into the project by which we can get an understanding from the coastal engineers, from the people at the Ministry of Works as to what the finalized bridge design is like, before I can tell you what the height is likely to be, because we are aiming to put the radar on the bridge itself, if that answers the question.
Excellent. Thank you, Brandon. The next question I'll go to is, how does the early warning system integrate with other disaster management systems in the Bahamas?
So this now would call into our partners. I've mentioned that we want to do this work with the Bahamas Meteorological Department, yes. But we also have the overarching Disaster Risk Management Authority, who will run, let's say, from a policy perspective, that interconnection between the work of the Glass Window Bridge and every other stakeholder with regards to disaster risk management. And so that is what we intend to do. We will take the DRM's lead on this matter.
Excellent, thank you. Ian says, excellent presentation. And Gregory says, great presentation. Greg Thompson from the Department of Meteorology here in the Bahamas would love more info on the SWAN model. And I understand that the Bahamas has a working model that they also use sail drones. Could that not be implemented also?
Absolutely. Anywhere that we can get data from, we'll absolutely take it. If you want to get more details on the wave model, I can, if you email me, I can provide the full text of the article to you. But feel free to reach out to me in the university, and we can most certainly have a conversation on how the wave model was implemented and how we plan to improve it in the future.
Excellent to hear. Ian has also come back and asked, what time frame are you looking at for the implementation of the model?
Are you referring to when I'm going to start running the model? Is that the question there?
Ian, would you like to just clarify there when you are? Yes, he says yes.
Yes. Okay. So I think the best way to answer that is that once funding comes through to purchase the computers, we're going to set the model up and have it running, let's say, maybe a month after that. So really and truly, give us a month's worth of time. Once we have the funding to do it, and we should have that hopefully by the end of this year. 1 month after that, then we can begin right away.
Excellent, good to know. The next question says, for you to get the distance described, you should have a certain distance above sea level. What would that height be?
Again, that is going to have to wait until we can actually go into the field to make a determination. We could not possibly give you an answer right now. Unfortunately, the Bahamas, the Caribbean in general, is a very data poor area. And so we are pioneering quite a bit of what we have to do with the early warning system. But once we make a determination, all of these variables will be incorporated into what the early warning system will eventually be. And then we move from place to place. Those numbers will have to be tweaked and made local. So the best answer is, until we do the research, the answer is, and the appropriate answer is, I don't know.
That's a good answer. Thanks, Brandon. Gregory has also come back and said, a very good suggestion, suggests that cameras at that location also be introduced.
Oh, yes, those are most certainly going to be there. Not just, let's say, to ensure that we can validate that when our forecast say it's going to arrive at 2 o'clock, that the wave activity arrives at 2 o'clock and we can see it, but also cameras themselves will allow us to use AI tools to predict the wave activity from the optical images themselves. you're quite spot on, and we have full intention on doing just that.
Excellent. And Dr. Davies says, what is the data transmission method from the buoys, cellular or satellite?
Okay, so that is a very, very good question. Depending on if, let's say, local communication companies, their range can extend towards the buoy, then the cheaper and best option in that situation would be to use cell towers, yes. But in the event that we are slightly too far out to sea, then we'll have to use satellite. We intend to look at the 250-meter line of bathymetry, let's say to the east of the glass window bridge, but the specific location at that boundary line has yet to be determined. So we have to first find that line and then find out, are we within cell tower range? If yes, we use cellular. If not, then we'll have to use the satellite. But also, let's say we want to, let's say, have an option for both, so that if cell service went down for any reason, then we can have the satellite as a backup. And that is something that is very important to us.
Excellent. Thank you, Brandon. I think we've got time for a couple more questions. So if you have any, pop them in the chat or the Q&A. One question from me is, what kind of long-term maintenance and monitoring will be required to keep this kind of system operational?
Well, when we consider our designs, we are considering to get a robust buoy that once we put it in there, it'll stay there for 10 years. Something that we'll have to go and see, let's say, every 6 months to a year, just to make sure the sensors are working good, humidity hasn't destroyed anything. That is, say, more or less what we have to really keep our eyes and hands on constantly. But the radar then, because it is based on land, we can more or less set it up and just leave it right alone. Now, from the observational platforms, that's the situation there, but the computers are a lot more tricky. You would have situations where data transfer for one reason or another just didn't occur. That's going to be a day-to-day kind of thing. And so the idea now is that we would want to initially host this activity at the University of the Bahamas, yes, but I can envision that a full-time oceanographic institute will be required, not just to monitor and maintain the system at a glass window bridge, but for the eventual dispersal, the replication of these systems elsewhere, both in the country and in the region.
Excellent, that's good to know. Thank you. Dr. Davies again asks, would it be possible to integrate the swell measurement devices into boats or motor vessels paired with GPS technology to create an adaptive network?
Technically, yes, but practically, no. Because of course, if you have the heavy swell events and the boats are there, well, now we have one more set of people to go and rescue too. So I typically wouldn't want, let's say, a boat to be out there in those conditions. A good example would be during Hurricane Joaquin in 2015. There was the El Fargo that was out in the open ocean during, let's say, heavy swell activity. That boat sank. So those were lives lost. That was the boat lost. So can we put sensors on the boats? Yes. Should we put sensors on the boats? No.
Thank you very much, Brandon. Gregory says, yes, boats cannot take the swell action out there, and also says, your ideas are well put, and I do hope you get to implement them. I'm concerned about the funding, though, of this, but I'm sure you've thought this out. This is badly needed.
Well, in terms of funding, we hope to secure about $750,000 from the Caribbean Development Bank. It is a part of the, let's say, the reconstruction of the Glass Window Bridge project entirely, but we do have quite a few other options in terms of where can we acquire funding to continue the program and expand it. So, for example, you have the SOFF. Let me see if I can find the acronym for you. I have unfortunately forgotten it. Oh boy. 1 second. SOFF. One moment. Yes, you have the Systematic Observations Financing Facility, where throughout the region, they look for projects like this to build early warning systems for low-income or medium-income countries. And so while we are not necessarily eligible now, hopefully with the success of this project, we can, how to say, convince them to change their minds.
Yes, fingers crossed for you there. Dr. Davies comes back and says, but can the boat support a baseline data collection and swell data below catastrophe level?
Now the answer has changed. Now the answer. So we do have a project now that's looking at getting oceanographic temperature data from fishermen. So when they go out to do what they have to do, they go and take those measurements. So if we can have a similar program, then absolutely. But that now means that we'd have to have a sensor that is going to take those wave activity measurements when considering ship movement, because that will change the answers for you. So let's say, for example, if you're traveling along with the waves, right? You wouldn't experience wave breaking as you normally would if you were traveling against the waves. So we have to find a way to make those measurements while the ship is in motion, because we cannot expect, let's say, fishermen or whomever is out there to go and sail 10 miles, sit there and wait until 10 hours, until 10 hours of observations have been made before they move again. That would be unreasonable.
Excellent, thank you, Brandon. Just quickly, Ian has asked if I can drop the name of the funding agency in the chat for the early warning systems. Did you say it was SOF, and what was the other one?
So not SOF, it was the Caribbean Development Bank.
There we go, Caribbean Development Bank. Ian, I hope that
Yes.
helps. I'll pop that into the
Yes.
chat as well. I will go.
With that said, we want, let's say, to potentially approach the systematic observations financing facility for additional funding.
Yeah, hopefully you will be able to go through that process. I will quickly go to Mark's question and then I'll finish it off there. But as I mentioned earlier, if you do have any questions that you haven't managed to ask Brandon, you can reach out to me and I will ask Brandon if he's happy for me to share his email as well, or possible contact.
That's not a problem. That's not a problem.
Brilliant. So what I'll do after this session is I will share the recording, and if I can grab the PowerPoint presentation off you, Brandon, as well. I think we've got a number of eager people who would love to see that. But for now, I will go with the last question from Mark, who says, great talk, Dr. Bethel. How keen are the UB students to be involved with field work? Can they do their final year projects with the data?
That is something I think has just triggered the nerd in me. Absolutely. I have an oceanography class right now, and I've mentioned to them that at the end of the semester, I will hope to choose the best 2 or 3 of them. And this now is something that they can go and build a career out of. It's not just, let's say, in terms of doing the forecasting, yes, but you could now imagine that if you're having 24/7, 365 observations of the ocean, it then means that the waves, that's a research paper. The currents, that's another paper. The tides, whatever variable that tickles your fancy, bring your ideas, here's the data, and let's get to work. Absolutely.
Excellent. I think that ties back to a conversation Brandon and I were having before this session about the next generation of meteorologists, hydrologists, and researchers, and how it's important to make sure that this is not something that people age out of, and that those spaces are being refilled and our Met services can continue to run. So thank you very, very much, Brandon, for today. I think people have really enjoyed hearing from you, and I'm sure once I share your details and the recording and the presentation, you will probably get some people reaching out for some more information. So thank you again, everyone, for attending, and thank you, Brandon.
Yes, thank you for the opportunity. Just briefly, if there are any individuals who are interested in, let's say, contributing, to doing the research partnerships, please, I am waiting for your call.
Excellent. That's what we're here for. So do reach out, make those connections. And as I put in the chat as well, our next webinar is going to be based around cloud optimized AI-based rainfall forecasting over the Greater Horn of Africa. And we have speakers from IGAD and Oxford University. So do look out for that webinar in a couple of weeks' time. It won't be next week because myself and the team are going to Vanuatu for the Pacific Meteorological Council. But keep an eye out for that next one, and we'll all see you soon. Thank you very much.